there is someone standing at a crossroad. And in a sense, we can start there looking at coordinates in the real world. Particularly Salt Lake City is wonderfully laid out like a grid. And you can tell someone they're at a particular street corner, and you can determine exactly where in Salt Lake City they are. And to some extent, Tucson is like that. Let's take a look. This is a map of the center of Tucson, and I've shown the intersection of Broadway and Stone here. The reason I've done this is the geographical center of the city. Stone Avenue cuts up and down, north and south through Tucson, and it divides east and west. If you're on Broadway and you're going, what is on this map, to the left, you're going west. If you're going to the right from there, the addresses will be east. Similarly, Broadway divides north and south. If you're north of Broadway, you can go north of Broadway or south of Broadway. So Stone Broadway is the 0, point. It's the, at least according to the streets, the dead center of Tucson. And I suppose at some time in the past that used to be, but of course Tucson has grown now. Let's look at how this grid-like system works. This is another section of Tucson, and for example, I could say I'm standing on a corner here of East 19th and South 6th. And you can, if I told you that, you could visualize the grid and go exactly to that street corner by using those numbers. If I wanted to, I could, for example, tell you there's West 18th and South 6th. I can determine points on that grid by numbers. And if I wanted to really, for example, suppose there's a point there, I could overlay the Tucson map with an actual grid where I can talk about South 6th, South 5th, South 4th, South 3rd, West 16th, West 17th, West 18th, West 19th, West 20th. There's a grid that's labeled effectively by numbers, and you can think of east, west, north, south being equivalent to positive and negative on the number line. There is what almost is effectively a mathematical point, the corner of South 6th and West 17th. We have maps to guide us geographically. We can use the same kind of map idea to guide us mathematically. And we owe this to a French mathematician, René Descartes. And he was the one who developed the idea of looking at geometrical figures in a mathematical way by looking at what numbers they generate when they're laid down on a coordinate system. He, incidentally, is the philosopher responsible for the very famous phrase, "I think, therefore I am." But more important to us, he developed a system of science of numbers of geometry called analytic geometry, which describes mathematically circles, ellipses, and of course what we're paying attention to in this class, straight lines. And he developed a system of coordinates called the Cartesian, after Descartes, coordinate system. What I'd like to point out now is some of the vocabulary involved with navigating this particular mathematical map. First of all, you'll notice two principal lines that are horizontal and vertical, 90 degrees to each other. These are called the axes. Each individual one is called an axis. The horizontal one is called the x-axis, and you notice we've labeled it with an X. The x-axis is always horizontal. The vertical one going up and down is labeled the y-axis. And you know that there is a 0 point, a center, where this grid system starts. That's right there. And the name for that center, the 0, 0 point, where x is equal to 0 and y is equal to 0 is called the origin. What we can do is know that if we know an x value and a y value, you notice we say coordinates, the ordinates together, the positions together, because if I just told you x or just told you y, you couldn't determine an actual point. I need to give you those two intersections. Therefore, we use the word co. And for example, suppose I have a point there. I can describe where that point is by giving you two numbers. I can give you an x value and a y value, and it's often written like this. In this case, I can say that this point can be described mathematically on that coordinate plane by the numbers 2, 4. These numbers are called an ordered pair. The reason they're called an ordered pair is you need to know that the first number is going to tell you where you go horizontally. It's always the x number. The second number is going to tell you where up and down you go. It's the y number. And whenever we write an ordered pair, we write it in that xy style so that anyone else who looks at this subsequently is going to know what you're talking about. And in order to actually find that point, what we do is to find the x point, we go over 2. In other words, in this case, since it's plus 2, we go 2 to the right. If that were negative 2, we would be moving to the left. Then it's 4, y is equal to 4, so that description tells us to plot the point. We go over 2 and up 4. And that's how we get to that. Typically, what you want to be able to do is, if someone shows you a point in the Cartesian system, you should be able to examine that point and write down the coordinate pair, the ordered pair, or given an ordered pair, you should be able to find where that is on that coordinate system. Now, in order to determine the coordinates of a given point, here's what you do. You determine where it falls in relation to the x-axis, whether it's a negative number, meaning you're going to look to the left, 0, where you're right at the center, or a positive number where you look to the right. That's your first coordinate. Then you look at the y-axis. A negative number is down under the x-axis. A 0 is right along the x-axis, and a positive number means you're above the x-axis looking up and down. And here's what you remember. In other words, you have crossroads. Y goes up and down. X goes horizontally. And you determine a position by giving a pair of numbers, x first, then y. And you'll see these numbers always written in brackets with an x value, 3, comma, and then a y value. Let's look at how we would actually plot some of these coordinates, and we'll practice a little bit. It's not very difficult. You just have to be careful that when you're working with this, you count carefully or you might get messed up. Let's look at some examples. How about 4, 3? How do we plot that? X is equal to 4, so we go 4 to the right. Y is equal to 3. We go 3 up, and then the point goes right there. Let's try another one. How about -3, -4? The -3 indicates that we go along the x-axis in the negative direction to the left 3 units. We go to the left 3. At this point, we could go up or down, but the coordinate for y is -4, which means we go down 4 units. And here we plot the point. Bam, there's where that point is. We've plotted 2 points by going first along x, along horizontally, and then vertically up and down depending on what the y value is. Let's look at a few more. How about 0, 3? That tells us, the 0 tells us that we don't go anywhere along the horizontal axis. We're right at x equals 0. Then we see that the y value is 3. That says we go up 3 and plot the point, put the point there. 0, because x is equal to 0, we just go straight up and put the point at 3. -4, 0. This tells us that the x value is -4, 4 units to the left. The y value is 0. We don't go up or down this time, so that when we plot this, we just go 4 units to the left and bam, stick in our point. Let's practice. Let me give you a few. I'll take a couple of seconds and let you try to decide where that point goes, and then I'll put it in. 4, 7. What does this tell us? We do what? We go 4 to the right along the horizontal axis, along the x-axis, then we go up 7, and the point is right there. 3, 0. This tells us we go 3 to the right, but we don't go up or down because the y value is 0. Let's try one more. -3, -5. This tells me I go along the x-axis -3, which is 3 to the left, and then the y value is -5, so then I go down 5 units and plot the point there. Now, this actually looks like very, very theoretical, no particular use for it. But remember, in Unit B, again, we were looking at charts. And this kind of plotting can be useful when you want to show people information that depends upon particular measurements over time, or to compare two different quantities together. Here's an example. Suppose I want to compare how much I spend on advertising with what the with how much money I make, how many sales I make. What I can do now is say, all right, what happens if I spend $1,000 on advertising? Then I would make $50,000 in sales, and I plot a point at that intersection so that 1,000 is my x-coordinate and 50,000 is my y-coordinate. And I continue to do this. If I spend $2,000 on advertising, I make $75,000. Notice how I plotted that. It's somewhere between, halfway between 50 and 100, but I don't have the grid fine enough. At 3,000, if I spend 3,000, I make 150,000. If I spend 4,000, I make 200,000. You see how I'm using the Cartesian coordinate system to indicate information to people in a way that is a lot stronger and a lot more interesting than just plotting numbers. And to really drive your point home, often a good thing to do is to connect those points with some kind of a line. Now, I can look at that graph and see immediately that as you spend more money on advertising, you're going to make more money in sales. On the other hand, if I look at that list of numbers over there on the right, it might not be quite so obvious to me what's going on. Plotting coordinates for the purpose of illustrating a trend or a growth is a very useful technique when you're trying to show someone, when you're trying to get ideas across very quickly. Let's outline the procedure just to review it. For the x, you go right if it's plus, left if it's negative, whatever the units are that are indicated in that first number in that ordered pair. For y, you go up if it's positive, down if it's negative, and then you plot the point. Very straightforward procedure. Now, we can also talk about quadrants. We can divide that grid up into 4 separate areas depending on what the relative xy quantities are. And that's often useful in talking about these mathematical quantities. There's the xy grid without the particular lines, and we just want to talk about quarters of it. This is called the first quadrant, and in this quarter everything is positive. X is positive going to the right, y is positive going up, and anything I plot in that quadrant will have both positive values. Proceeding around, the second quarter is called the second quadrant. Notice if I plot a value in that quarter of the graph, the y values will be positive, but the x values will be negative. There's the third quadrant, and if I plot anything there, both the x and y will be negative. And here, x will be positive, but y will be negative. Those are the 4 quadrants, the first, second, third, fourth quadrant. What we can, as I indicated before, we can look at the general values of the ordered pairs in each of those quadrants. In the first quadrant, both the values will be positive. In the second, the x value is negative. In the third, both the x and y value of the ordered pair is negative. And in the fourth, the x is positive, but you're going down in y, so that's negative. What quadrant, if I had 5, 4, what quadrant would that appear in? That would be quadrant 1. If I had minus 5, 4, x is negative, that would be in quadrant 2. If I had minus 5, minus 4, they're both negative values, that's quadrant 3. And if I had 5 minus 4, x is positive, y is negative, that would be in quadrant 4. Here's one. What about 5, 0? That's going to be right on the line of the y value. It'll be right along the x-axis. And we say that this point is not in a quadrant because it's right on one or the other of the axes. Just to review, here are what the relative values are for each of the quadrants. And we can also say that if this is the case, if we have a value that is lying up along the y-axis, in other words, x is 0, or the other way, that is not in a quadrant. Let's do a little quiz. How about 2080? What quadrant? Quadrant 1, both positive. 10 minus 200. There, y is negative, x is positive, quadrant 4. X is negative, y is positive, quadrant 2. X is positive, y is negative, that's quadrant 4. I'm sure you get the idea of this very quickly. Let's change topics now. Oops, I missed one here. How about minus 40, minus 500? Both are negative. I should have known that I left out an important quadrant, quadrant 3. Now we'll go on. What we'd like to do now is look at the distance between 2 points. For example, here's a point 1, 1 and 5, 1. And what I'd like to know is what is the distance between those 2 points? And you see, since they're both at the same y position, I can see that the distance is the difference in the x-coordinates. And in fact, if I count blocks, I see that there are 4 blocks between the 2 points. So the distance between the 2 points is 4 units. Notice I can take 5 minus 1, the 2 x-coordinates, subtract one from the other, and get what that distance is. Let's suppose we have point x1 at 1, 1. And point x2 at 5, 1. Let's be a little bit more formal about this. I look at the distance, it's point x2 minus point x1. 5 minus 1 is 4 units. Here's another example. Here's a point where I have minus 5, 2, and here's another point, 5, 2. And I've pointed out x1 and x2, and I'd like to know the distance between them. And of course, the easy way to get the distance is just to count the number of squares, and I can see right away by counting the number of intervals I need to go. That's going to be 10, but let's look at the formal way to do it. What we want to do is we can take the distance as x2 minus x1. 5, and then since we have minus, and minus a minus 5, minus a minus is a plus, so I see there the distance is 10. If I take an x1 minus x2, all that would have happened is I get minus 10. Typically, when we express distances, we express them as the absolute value. In other words, just how far you go, regardless of the sign. If you get a negative sign when you take a distance, just throw the negative number away. Take the absolute value, because when you talk about a distance, it's a positive number. And we say, in this case, the distance is 10 units. Let's turn this around on its side and take two slightly different points. There is minus 5, 2, and minus 5, minus 4. Notice in this case, the x-coordinate is exactly the same, but y is different. So instead of having a horizontal distance, now I have a vertical distance, and the difference is going to be the difference in the y points, not the difference in the x points. If I look at the distance, it's going to be y2 minus y1. y2 is 2, y1 is minus 4. 2 minus a minus 4 is going to give me 6. And of course, as I said, I could get that by counting units. What now about two arbitrary points that aren't exactly horizontal or exactly vertical? We have to make use of the Pythagorean theorem, which we've discussed in earlier classes. Remember, for a right triangle, it always holds that the square of the longest side, the hypotenuse, is equal to the square of one side plus the square of the other. The square of the hypotenuse is equal to the sum of the squares of the other two sides. Ask me to say that fast. But for example, c squared, the square of the length of the longest side, is going to be 3 squared plus 4 squared. If I work that out, I get c squared equals 25. Taking the square root of both sides, I find that the long side equals 5. This is exactly what we do when we look for the distance between two arbitrary points. And if c squared is equal a squared plus b squared, we need to take the square root of the sum of the squares to find that distance. This is what we're going to do here. First of all, we'll take 2 points. There's the point 1, 7. Here's the point 5, 4. And what we'd like to know is, what's that distance d? In order to find it, we need to know the x distance and the y distance. We need to determine those two, and then we can find d using the Pythagorean theorem. Here's what we're going to do. We see that the difference in the x is x2 minus x1, in this case 5 minus 1, and similarly y2 minus y1, 7 minus 4, we need to square those. Here's how we do it. The first thing we do is determine what the x distance is. Then we determine what the y distance is. Then we apply the Pythagorean theorem this way. And 5 minus 1 is 4, 7 minus 4 is 3. I use the more complicated form of that theorem. Then I have d is equal to 4 squared plus 3 squared. Then I do the square, add them together, and in this case I find the distance between those 2 points is 5 units. Let's try another example with different points so you get the procedure for how to do this in general. Suppose we have a point -3, 6, another point 4, 2, and I want the distance between those 2 points. I need the x distance and the y distance, and I need to remember that formula. I calculate the x distance, again as 7. I calculate the y distance as 4. Then I can use the Pythagorean theorem. Adding 7 squared plus 4 squared gives me 65, and in this case I have to use a calculator because it's not an exact square, and I find that distance d is approximately 8.06 units long.